Okay, let's unpack this. Have you ever looked up at a jet streaking across the sky and wondered what truly gives it that incredible, effortless power? It's not just the fire and the roar, it's actually the air itself and how brilliantly it's managed. Today, we're taking a deep dive into the unsung hero, the absolute beating heart of every gas turbine engine, the compressor. And if you're like many of our listeners, gearing up for those crucial ATPL theory exams, consider this deep dive your ultimate shortcut to mastering these complex systems.
Precisely. The compressor is, in every sense, absolutely fundamental. It performs the crucial and often underappreciated task of preparing the vast quantities of air for combustion. Without efficient compression, without squeezing that air to the right density and pressure, the entire process of generating thrust would be, well, impossible. Our focus today is to demystify these intricate systems, turning what might seem like overwhelming technical details into clear, actionable knowledge. We'll cover the what and the why, and crucially, we'll give you the framework to understand how this information is likely to appear in your ATPL exams. This isn't just about memorizing facts, it's about understanding the core mechanics that literally lift us into the sky and ensure safe, efficient flight, and being able to recall those facts with confidence when it counts.
Our mission is crystal clear. We're going to navigate the core principles, explore the different types of compressors, diagnose the potential issues that can arise, and then marvel at the clever engineering solutions developed to keep these powerhouses running smoothly. You'll walk away not just understanding what these components are, but deeply grasping why they matter and how to use that knowledge to confidently tackle even the trickiest exam questions. Get ready for some genuine aha moments that truly stick with you. So, before we even think about introducing fuel or creating that controlled explosion, we have to talk about air. Why is this initial compression step so utterly vital for these engines? What's the fundamental purpose that underpins everything else?
It's fascinating, isn't it? The very first non-negotiable step in producing any thrust from a gas turbine engine relies entirely on this meticulous air preparation. Imagine trying to start a bonfire with a gentle puff of air versus a powerful blast from a bellows. You need that concentrated oxygen. Similarly, the air must be compressed and compressed significantly before any fuel is introduced into the combustion chambers. This dense, high-pressure air is what makes the subsequent fuel ignition and expansion so incredibly efficient, giving us the immense power we see from jet engines. This process also has a built-in feedback loop, because the main compressor types we'll discuss are themselves turbine-driven, connected by a robust shaft, meaning the power generated ultimately helps compress more air. It's a self-sustaining cycle of power.
That truly sets the stage. So if we're going back to the pioneers, to those early days of jet propulsion, they didn't have the luxury of the highly advanced multi-stage axial designs we see today. They often relied on something called the centrifugal compressor. What made that particular design the go-to choice initially, and what was its ingenious yet perhaps simpler approach?
The centrifugal compressor was indeed the workhorse of early gas turbine engines, and its design reflects a kind of robust simplicity. Its mechanism is quite straightforward. A turbine rotates an impeller. You can think of it as a high-speed, very strong fan with vanes, where air enters its center, often called the eye, guided by rotating guide vanes. As this air is continuously drawn into the impeller, centrifugal force takes over, flinging it outwards towards the impeller's tip. Now, crucially, the vanes within the impeller aren't just flat, they have a divergent shape, meaning the passages between them gradually widen. This design causes two important things to happen simultaneously. The pressure of the air increases as it flows outwards, and because mechanical energy is constantly being added by the spinning impeller, the air's velocity also increases significantly.
Okay, so it gets flung outwards, gaining speed and some pressure. Then what happens?
Right. After leaving the impeller at high speed and pressure, this air then enters the diffuser section. This is a stationary component, but just as vital, comprised of fixed divergent ducts. The diffuser's role is absolutely critical. It takes that acquired kinetic energy, that very high velocity, and converts it into potential energy, which we experience as a further substantial.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.